This is Professor Corey from the Professor's DuBois. In this video, I will demonstrate how to solve problems involving the two-point version of the Clausius-Clapeyron equation. In these problems, P represents vapor pressure, T is temperature in Kelvin, delta H is the heat of vaporization, and R is the ideal gas law constant. You will use the equation to solve for either a vapor pressure, a temperature, or the heat of vaporization. I will perform an example of each. All of the algebra shown in this video can be applied to solving the Arrhenius equation, so let's get started. In this problem, we are asked to calculate the vapor pressure of water at 50 degrees Celsius. What I'd like to do initially is to extract the data from the word problem. This is shown in red. I've converted the temperatures to Kelvin, and I'm using the gas law constant that contains the energy unit in joules. Next, I will enter the values in the equation, as shown in blue. There are many ways to solve this problem algebraically, and what follows is my approach. The first step that I will perform is to rewrite the natural log as natural log of P2 minus the natural log of the denominator. This is a log function. If we have the natural log of a fraction, this can be rewritten as the natural log of the numerator minus the natural log of the denominator. The next step is to take the natural log of 23.8 using our calculator. Be sure to use the LN button and not the LOG. The value is 3.1697. This has been rounded, but contains more significant figures than the data provided. You may notice that I included units initially, then removed them. I recommend setting up the equation and including the units to make sure that they will cancel. You can see here that our answer will be in atmospheres. For the next step, I will divide the heat of vaporization value by the gas law constant. A common mistake here is to forget the negative sign. Then, I will perform the division within the parentheses. It's important to keep all the digits in your calculator on this step, as rounding here can have a significant effect on the result. I will subtract these values and then multiply, keeping all of my digits. Now, I will start isolating P2, or the vapor pressure. First, by adding 3.1697 to both sides. This will cancel on the left, and what remains is the natural log of P2 equal to a value. In order to isolate P2, I will have to take the inverse log of both sides. This eliminates the natural log, leaving P2 on the left, and you will use the inverse ln function on your calculator for the value on the right. This is typically done with second function ln. Be sure to use ln and not log. Our vapor pressure is calculated as 84.9 atmospheres. I always ask myself if my result makes sense. In other words, would I expect the vapor pressure to be higher at higher temperature? I would, and the result appears reasonable. If I obtained a result that was lower than 23.8, I would be certain that I made an error. This would most likely come from forgetting that negative sign for the heat of vaporization over the gas law constant. The problem contains the same data as the previous problem, except both vapor pressures are given, and one of the temperatures is now the variable to be solved for. If we do the calculation correctly, the answer should be 50 degrees Celsius. Again, I've written the data from the problem off to the side, and then inserted these values into the equation. I'll begin this problem by simplifying the left side by dividing 84.9 by 23.8 and then taking the natural log of my result. This is ln. Next, I will divide the heat of vaporization value by the gas law constant, making sure that I do not miss that negative sign. Now, I'll divide both sides by the negative 4895.357. This cancels on the right and produces a negative value on the left. I can divide 1 by 298 on the right to eliminate one of the fractions as well. My focus now is to isolate the T2, so I will add 0.003355705 to both sides of the equation. This will cancel on the right, leaving 1 over T2. I have to get T2 out of the denominator. The way I will do this is by multiplying T2 on both sides of the equation. This cancels on the right, leaving just 1, and puts T2 on the left. To isolate T2 on the left, I'll divide both sides by the 0.003095908. My answer is in Kelvin units, so I will have to subtract 273 to get the answer in Celsius, and the answer is 50 degrees, as we expected. This time, I'm going to solve for the heat of vaporization using the same values. Let's see if we can get 40.7 kilojoules per mole. I'm using the same approach. Extract the data from the problem, shown in red, enter these values in the equation, make sure the units cancel out. I will begin by dividing 84.9 by 23.8 and taking the natural log. This is the ln button on your calculator. Next, I'll divide the values in parentheses, eliminating the fraction. It's really important that you do not round these results. I can perform the subtraction in the parentheses, which results in a negative number. Now, I will divide both sides by the negative 0.000025973. This will cancel on the right and produce a negative result on the left. Lastly, I'll isolate the heat of vaporization by multiplying both sides by the gas law constant. Our result is, as expected, 40.7 kilojoules per mole. To summarize this approach for these problems, first, extract the data from the word problem with units. Next, enter the values into the equation and make sure that your units will cancel. Then, you have to work toward isolating the unknown variable. There are many ways to do this and get the correct result. Hopefully my approach is useful for you. Thanks for watching. Stay tuned for additional support with chemistry problems and general chemistry.